By the way, the slides you can download here at this link. I will provide it again if you need to. Here are the main collaborators that led to the work on this presentation. So as you can see, there are quite a few people, and I would like to thank all of them at this time. Okay, so before we talk even about any discretization method, I think it's very useful to go back to what we mean by mathematical modeling. I will assume today that we talk about mathematical modeling using partial differential equations. So nothing that has to do with discrete systems, although there are some similarities, or agent-based models. These are models that are based on the discrete set of particles or points or agents that have interactions with them, with each other. Here we're only talking about problems that can be written in a continuous form. So we assume that we make the assumption of continua according to Cauchy. So this is here the continuous problem. So let's take an example. Here I took an example from human body, but it can be an example from aerospace or for bridge engineering or dams or whatever topic you think about. At some point the problem has to be defined. So here we have the tongue of someone, and we are interested in trying to simulate speech. Here we have a target area in the brain, and we are interested in removing this target area or in inserting a needle that reaches to this target area. So that's the problem we're trying to solve. So these problems are continuous problems, but for now we have nothing about them. So the first thing we do is we write a mathematical problem. If we take the case of the tongue, which is this material in the mouth that is able to contract, it's a muscle, it's therefore an active material. It's got muscular activation, and it also has a passive part. So therefore the stress can be written as a sum of passive plus muscular activation. Depending on the fiber direction, you can write the muscular activation part beta T EA cross product, with tensorial product with EA. So essentially you know how to write this. At least, of course, you think you know. This is an assumption. Well, because of course the tongue does not behave exactly as you think it does, and it certainly does not behave as simply as this very little simple example tells us. This is an assumption. So we make assumptions, a lot of assumptions in a mathematical model. Now if you take another example just to show how we go about modeling things, if you take here, for instance, the artery in your body, you see that there is the lumen here, which is basically where the blood goes through. Here you have the plaque, and here you have the necrotic core, which basically is dead body, right? So now the problem is that now you have this region of interest because you would like to avoid that the plaque actually breaks. So if that thing breaks, you may have rupture, and then this creates rupture of the plaque, and therefore can create embolism. So that's very negative. So what you try to do is you try to see how you can simulate this. So of course you need to have a region of interest, because here you will like to measure the stress, for example. But on the surrounding here you have, for example, again, fixed boundary conditions. But this is an assumption. The boundary conditions for sure are not fixed. There is some sliding, there is some contact, some friction, and so on. So we need to make assumptions. So boundary conditions are also assumptions. And then the discrete problem is found. Once you have the mathematical model, we can find a discrete problem in many ways. Yesterday we talked about point collocation, where you only write the partial differential equation at the points, and you do not use any numerical integration technique, so no averaging. Or you can write a finite element problem, which is a Galerkin problem, which is a essentially weighted residual approach. And you can discretize the domain. So you again make another assumption here because of the geometry. So the geometry now is supposed to be carried by the mesh. As we discussed, the mesh has three purposes. One is to describe the geometry, two is to describe the approximation, three is to perform numerical integration. So with these three things, the finite element mesh allows you to cover the whole domain. And this is sometimes difficult. If you look at the bottom left here, this brain meshed with hexahedral elements or hexahedral dominant in collaboration with Bruno Levy at INRIA. This is quite nice because with hexahedral mesh generators, you can decrease the problem of tetrahedral elements, which we can go into, essentially locking over stiff behavior and so on. And there are many other approaches you can do that with, for example, smoothed finite elements or double interpolation methods and so on. So lots of methods. Or you can use also a meshless brain. In that case, it's a bit cheating because we created the meshless brain from the mesh, which doesn't have a lot of impact. But what we could do is create this meshless brain using point collocation approaches like yesterday, and immerse the brain into a background mesh, and then simply put the points on the boundary and then try to see if we can solve that. In particular, to do using material point method, for example, self-contact of the brain sulci here, which I think is a super tough problem that a lot of people would like to work on, in particular for dynamic impact on the brain, for traumatic stress injury, for example. Okay, so, and then finally, once we have this discrete problem and we can discretize the whole plethora of ways, what we have to do now is we have to solve the problem. So we need a numerical solution. This numerical solution is found by usually inverting one matrix if it's a linear problem, or a sequence of matrices if it's a nonlinear problem, and we linearize the problem. Okay, so basically now we have a numerical solution. It looks like a beautiful array of colors like we have here. And if you're not colorblind, which I am, then you can recognize where things are. But this very nice color bar was chosen for colorblind people so that I have no problems looking at it. It's always beautiful. Okay, so now what do we have here? We have problems, right? Because the first problem is, as we said, that the tongue definitely does not behave like a hyperelastic material with activation. It's much more complex than this. It's heterogeneous, it has some tangents, it has a lot of things associated to it, and therefore you need to be really careful in the way you do things, right? So that's also something to know. So first of all, the model is not right. There is a difference between the two. And this is called the model error. This is what does the model know about the real problem, about real life. And usually it knows far less than we think it knows, because we have a different physical problem, different constitutive model, and different material parameters. Okay, so then what's next? Well, then the geometry and the boundary conditions are also incorrect, because of course, as we said, there is some friction, there is some contact, there is some sliding and so on, and these need to be taken into account. One cannot only assume that the artery is fixed, for example. This is clearly not the case. And finally, and this is what we'll be interested in today mostly, we have a discretization error because we solve the mathematical model using a discrete set of points, which you see here. Either the nodes, if you have point collocation, or if you have mesh-free methods, or if you have finite element methods, you solve that thing, and that thing, of course, is not perfect. You will get some sort of error. And the big question is, and we'll talk about it again today, quite at length, is how do we compute the error, although we don't know the exact solution, right? Because if we knew the exact solution, we would simply compare the discrete solution to the exact solution. But of course, in the case that are of interest to us, we don't know this. So what we usually do is we test our method on cases where we do know the exact solution, and we hope that this solution is in a certain space, in a certain class of functions, in a function space, which is, let's call it smooth enough. So by smooth enough, everybody understands that it means that the solution can be differentiated a certain number of times and still remain smooth. So for example, if you take a sine function, you can take a cosine function. These functions can be differentiated infinitely many times, and they remain continuous. The differential of the derivative of the function is continuous, the derivative of the derivative is continuous, and you can go on and on forever. Polynomials are also like this, and there are, of course, harmonic functions are like this. You can take the second derivative. This is Laplace equation, for example. So, you know, you have lots of very smooth functions. The problem is that sometimes the solution is not smooth. And this is the case when you solve problems with fractures or discontinuities or interfaces and so on. So this is also something that will be the topic of today's discussion. And I would really like to emphasize that when we do a verification, so this is what we actually do, you know, we solve the problem, we have all these bytes that are coming in and out of the computer and trying to understand what's going on. We get now a numerical error on top of that because, of course, we cannot solve the equations exactly. So we are going to have some numerical round-off error, which will depend on the CPU you use. So if you use my computer or my friend's computer, you will get completely different results usually because of the round-off. And of course, if you have 32 bits, you will get more error than if you have 64 bits. We don't know yet what will happen with quantum computing, but this is a topic that at the University of Luxembourg we are very interested in. And there will be some new professors coming in the field of quantum computing very soon. And I look forward to working with them on defining new algorithms for computational mechanics in quantum computers. So that's another question. For now, we are interested in a very clear problem, which is what is the difference between reality and simulation? And typically that's what we see. We see only this difference between reality, which is this brain, and simulation, which is this overly simplified version of the brain with lots of assumptions on the material model, the boundary conditions, the forces applied, and so on. So we see only the total error, but what we would really like to do is to see the difference and the decomposition of this error into the discretization error and the model error. The numerical error usually we are quite happy with, at least as long as we are not on a quantum computer. I think things are relatively easy to delineate, let's say. So discretization error and model error are the two things we are trying to disentangle, and again this is very important to realize. And this happens all the time, that in papers people confuse model error with discretization error. They confuse verification and validation. So they are confusing the two questions. Are we solving the problem the right problem, or are we solving the problem right? So are we solving the right problem is the validation question. And are we solving the problem right, meaning are we solving the problem correctly, is the verification question. There is a very nice report by Tinsley Oden, unfortunately, who passed away recently, which explains this to the National Science Foundation in the US in order to explain why error estimates are important and why the USA should invest in this. We could discuss that later because it's a very mind-provoking and thought-provoking write-up. Okay, so now we know what validation means. Do we have the right problem? Do we have the right model? And verification, right? Okay. So of course, when we say do we have the right model, it doesn't mean anything outside of a very clear context. We need to say, do we have the right model for a certain quantity of interest? For example, if I'm interested in computing stresses, it might be that the model I need will be different as if I'm interested in computing temperatures. So for verification, it's the same question. What exactly is it that we try to measure? And this is really the key problem. We want this red label on both the problem and the solution to the problem. And finally, in certain cases, we are also asking the question, are we solving the problem fast enough? Because we are trying to get real-time results. And this is something highly important. Which I would like to come back to later, because sometimes having the solution too slowly means having no solution at all. This is something that I've understood by working with teams of computer graphics people that are working in the field of surgical simulation at INRIA in France. Stéphane Cotin in particular, I understood from him that sometimes having a solution too slowly means having no solution at all. And you can imagine very clear cases in robotics when you do control where this would be the case. If you're controlling a robot using a numerical model, if the robot cannot use the solution because the solution is not there, it's probably worse to have no solution than to have a slightly wrong solution that the robot can compensate for at the next time step. Okay, so this is a slide that is quite important to me. We talked about it yesterday, and we talked about the fact that if you zoom far enough into a material, you will always find some discontinuities. So you start from a car, you zoom down, you see the grains of the polycrystalline material that makes the solder joints of the printed circuit board. You zoom into an Airbus, you see these laminates with all sorts of carbon fibers running in all directions in order to make a material compliant in certain areas. And then if you zoom on a brain and you try to cut next to a sulci, for example, what you see is that you have discontinuities, interfaces, cuts, And these need to be taken into account. Now let's talk about meshing. So this is a paper which is now a few years old, and which was written by a friend of mine, Jean-François Remacle, that you probably know because with Geuzen, he is responsible for the creation of Gmesh, which everybody uses, I think. So he has been extremely impactful in the community through the creation of this piece of software which everybody knows and everybody uses. And recently he was able to generate with one machine in 1 minute 3 billion tetrahedral elements. So if you look here, you see that it was an Intel Core i7 Intel Xeon Phi with an AMD EPYC, and that was able to compute 3 billion tetrahedra in 53 seconds. So that means 55 million tetrahedra per second. And that's quite a lot, especially when people say that meshing is difficult and we should avoid it and it's not nice and it's a bad idea and so on. So I just wanted to highlight this because with Célestin Marot, Jeanne Pellerin and himself, he came up with this example. You can see here the meshing of a tire tread, which is quite impressive because at the end of the day you end up with 123 million elements. And this is computed in like 3 minutes. So clearly there is something that can be done about meshing, and this team in Belgium has done it. So it's really worth thinking about. Now, you could say, oh yes, but with multi-scale problem things don't work so easily because we have very thin structures that need to be meshed, and this is very difficult. Well, yes, it's difficult, but it's done. One machine, 1 minute, 3 billion tetrahedra. Look at this. You see in 114 seconds, you have, in 35 seconds, you have a total of almost 1 billion tetrahedra here. 721 million elements. So you see, this is quite a difficult problem, very difficult problem even, but it's done, it's solved. So of course, it doesn't mean that it will work in all cases, but the code that he built in his team is very robust and based on sound mathematical principles that help guarantee the generation of the mesh. Okay, so now why is that not sufficient? Maybe one could say, okay, but now you have linear tetrahedral elements. This is not so nice because you could have a stiff behavior like on this wonderful Rubik's cube, and you could have locking, which means that when you deform the element because of geometrical constraints, you are not able to get all the geometrical deformation modes, and therefore the problem is not solved properly and you get a lot of erroneous results. And well, I mean, that's true. This is what happens with linear tetrahedral elements. So what can we do about that? Well, we can do many things. So first of all, we decided to work with Bruno Lévy, who has an absolutely amazing generator of polyhedral elements. So you see these things here. They are not triangles, they are not cubes, they are not hexahedral in shape, they are polyhedral. So we can actually generate, thanks to his wonderful code, elements that are of polyhedral shapes. And as you know, the recent literature has been going in the direction of trying to improve the quality of the approximation in these elements. So for example, there is quite a lot of work done in polyhedral elements using various approximation schemes, in particular virtual elements, HHO, smooth boundary finite elements, smooth FEM. So we worked on all of them, and I think that there are quite some advantages to doing this, because what you can do is you can mix these little shapes together and you can make arbitrary shapes, like this femur, for example, which I have to confess is not the most complex structure you could think of, but in 2019 we were able to use smooth polyhedral finite elements in order to solve the problem of deformation of this femur. And this is done using Alice, which is this open code, and also with Claudio Lobos, who is in Chile and works also on mesh generation using hexahedral dominant meshes. So finally, you can also, of course, work on virtual element formulation of this, and we showed that a virtual element method is equivalent to the smooth finite element method in certain cases. So this is what we see here in this paper: virtual and smooth finite elements, a connection and its application to polygon polyhedral finite element methods with Sundar. We also worked on smooth finite elements, and you can read the details on this, in particular on the paper on the approximation in a smooth finite element method, because that actually gives a lot of details that are, I think, super important to understand. The basic idea of smooth finite elements, which I'm not talking about today, is to integrate over the boundary of the element in order to get rid of the Jacobian. So the idea is really very simple. It's essentially to use the divergence theorem and to transform all the first derivatives into products with the normals to the element, or with the normals of smoothing cells inside the element. So we worked on that significantly, in particular with Nguyen Hoan Hong, who is a colleague in Vietnam, with whom we've worked really a lot. Okay, and finally, there is the scale boundary finite element, which is a method which not a lot of people are aware of, but which I would strongly encourage to look at if you're interested in exotic approximations, because this is really allowing you to have both worlds present in one element. So you have boundary elements in it and you have finite elements in it. So you essentially, using scaling centers, you are able to solve semi-analytically the equation in one direction, and the other direction you use finite elements. So if you have a two-dimensional problem, it reduces to a one-dimensional problem. A three-dimensional problem reduces to a two-dimensional problem. There are, of course, difficulties due to finding the scaling center, which needs to be done in a convex hull. You cannot find a scaling center if you don't have a convex element. So, of course, you need to find ways around this. But of course, these things can be done, and the accuracy is remarkable. So for fracture mechanics, I have to say that this is the most accurate method I've seen. Even boundary elements, at times, for certain problems, do not compete with scale boundary finite elements. So I, again, strongly encourage you to take a look, and if you're interested, I'll put you in touch with Sundararajan Natarajan, who's professor at IIT Madras, Chennai, so that you can get in touch with him. It is a not so well-known method, but very worthwhile looking at. And of course, Chongming Song in Australia is also working on this, and I think it's worth thinking about. Okay, can you still hear me, because something broke here?
Yes, I can hear you.
Okay, good. I don't know why the presentation stopped, but okay. Thank you. Okay, so here you should see a slide entitled Avoiding Meshing Complex Evolving Interfaces Through Unfitted Methods. So this is what I will start by motivating the rest of the talk. So here, if you are interested in details, you can take a look at these three papers, which are the first time, to my knowledge, that people compute adaptive meshes for real-time simulations. So again, I repeat, what we do here is that we are able to, in real time, adapt the mesh to the problem at hand. So that, I think, had not been done. There was one paper in computer graphics that dated back to early 2000, where people had attempted this with extremely simple approaches. What we do is based on rigorous a posteriori error estimates that are backed by mathematical analysis that can show the convergence of the effectivity index and the convergence of the estimator to the exact error. So this is extremely, in my opinion, important to think about the error, the discretization error, during the simulation, in particular for real-time simulations where you would like to have control on the error, because here you are using very, very, very coarse meshes. Yesterday I was at a PhD defense in the afternoon, and the student of Adrien Courtecuisse, Zicure, was working on accelerating the problem of contact mechanics between several bodies in the body, right? And so he was working on contact, and he's now able to handle tens of thousands of nodes with thousands of contact points, all that in real time with multiple objects. That is amazing. And what is now missing is a way to compute the error for these calculations. Because if we can compute the error, we will be able to guarantee to the user that the precision of the work is at the right level. So that is, in my opinion, extremely important. So, as we realized, there are really two ways to handle interfaces. There is the first way, which is called decoupling the geometry from analysis on the right-hand side. And this is also known as implicit interfaces or unfitted methods. So what happens then is that the interface is not explicitly meshed, it's implicitly meshed, or it's implicitly represented using, for example, level set methods. And around the level set, you have some local refinement using octrees, but these elements do not conform to the interface. Contrary to that, where we decouple geometry from analysis, we have cases where we want to couple the geometry and the analysis. So that is the case in isogeometric analysis. And it's quite interesting to ask ourselves, okay, well, I mean, which of the two is going to help us more, depending on what we're trying to solve? And this is what we are trying to do today. So again, in isogeometric analysis, if we start from an arbitrary geometry, which is a propeller of a ship here, and we try to simulate, for example, the stress distribution inside this propeller. Well, yeah, there are two approaches. One is to create a mesh, which is the traditional approach, can take a long time, in particular for linear elastic cases, which takes almost no time to solve. Generating the mesh takes 80%, according to the 2005 paper of Tom Hughes, to generate the mesh compared to the whole solution time. So clearly, there are some issues. So now let's see what we can do. Okay, again, yesterday we talked about immersed collocation and generalized finite differences, and this is another approach where we are working and which I think could be helpful. Okay, so let's now delve into isogeometric analysis to try to explain what it means. So the idea is that you start from a geometry and you normally discard this geometry. So you get rid of it completely and then you get a mesh. But this mesh does not know anything about the initial geometry. For example, here, if you have a circle in the corresponding mesh, the mesh will never be exactly a circle unless you have circular elements, but these are very specific elements which are not straightforward to use. So typically you have no circular elements here, you have a polygonal or polyhedral representation, and of course you're losing the accuracy because here you have a perfect circle, here, well, I mean as perfect as you can make it using manufacturing, but here you do not have a perfect circle. So assuming that you want to model this perfect circle, and that this is a question because most of things you cannot model, you cannot manufacture exactly. So you have always a tolerance and little defects, right? But these defects are not what we're talking about here. Here we're talking about, in principle, if we had a perfect geometry, what would it look like? So the answer to that, it would look like a polygon. So what Tom Hughes said, okay, why not keep this circle and use it directly for the approximation instead of doing what we do here, using polygonal elements with finite element shape functions that look like Lagrange polynomials. Well, what we're going to do is we're going to use NURBS shape functions. Why? Because NURBS are used to build this initial geometry. So why discard them? Why not keep them? So this way, the approximation that is created by this circle or cylinder is going to be the one dictated by the NURBS. And as we will see, there are some advantages to that, but also some severe drawbacks, which we will discuss. Okay,